Download this code from codegive.com, link in the description below. Concurrency control in database management systems, a detailed tutorial. Concurrency control is a critical aspect of database management systems, DBMS. It ensures that multiple transactions accessing and modifying the same data concurrently do so without corrupting the database or violating data integrity. This tutorial will delve into the principles, challenges, and techniques of concurrency control, illustrated with code examples in a pseudo-sql and Python-like manner. 1. The need for concurrency control ****. Imagine a scenario where two users are trying to update the balance of a bank account simultaneously. User A checks the account balance, say $100, withdraws $50, and attempts to update the balance to $50. User B checks the account balance, also $100, since A hasn't updated yet, deposits $20, and attempts to update the balance to $120. Without concurrency control, the following might happen. 1. User A reads the balance, $100. 2. User B reads the balance, $100. 3. User A calculates the new balance, $100 to $50 equals $50. 4. User B calculates the new balance, $100 plus $20 equals $120. 5. User A updates the balance to $50. 6. User B updates the balance to $120. The final balance is $120, but the correct balance should be $100 to $50 plus $20 equals $70. This is a classic example of a lost update problem. Other issues that concurrency control aims to prevent include *dirty reads reading data that has been modified by another transaction but not yet committed, and might be rolled back. Inconsistent analysis reading different parts of the data at different times, leading to inconsistent results during aggregate operations. 2. Transactions, the building blocks of concurrency ***. A transaction is a logical unit of work that either completes entirely, commits, or has no effect, rolls back. Transactions have the following properties, collectively known as ACID. Atomicity ** all operations within a transaction are treated as a single, indivisible unit. Either all operations succeed, or none do. Consistency ** a transaction must transform the database from one consistent state to another. Isolation * transactions should operate independently of each other. Concurrent transactions should appear to execute in isolation, as if they were the only transaction running. Durability * once a transaction is committed, its changes are permanent, even in the event of a system failure. 3. Concurrency control techniques ***. Several techniques are used to implement concurrency control. The most common are locking * transactions acquire locks on data items, example rows, tables, they intend to access. Locks prevent other transactions from accessing the same data items in a conflicting mode. Timestamp ordering * transactions are assigned timestamps, and the DBMS uses these timestamps to order transactions and prevent conflicts. Optimistic concurrency control * transactions proceed without acquiring locks, assuming that conflicts are rare. At the end of the transaction, the DBMS checks for conflicts and rolls back the transaction if necessary. Multi-version concurrency control, MVCC. Each data item has multiple versions. Transactions read the version that was current when they started, avoiding conflicts. 4. Locking in detail ***. Locking is a fundamental concurrency control mechanism. Here's a more detailed look. Asterisk lock modes asterisk. Asterisk shared lock, S allows multiple transactions to read the same data item concurrently. Asterisk exclusive lock, X only one transaction can hold an exclusive lock on a data item at a time. This lock is required for writing, modifying, data. Asterisk lock compatibility matrix asterisk. Shared, S, exclusive, X. Dash 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 dash. Shared, S, compatible incompatible. Exclusive, X, incompatible incompatible. Asterisk locking protocols asterisk rules that govern how transactions acquire and release locks. Asterisk two-phase locking, 2PL the most widely used locking protocol. It has two phases. Asterisk growing phase asterisk a transaction can acquire locks but cannot release any locks. Asterisk shrinking phase asterisk a transaction can release locks but cannot acquire any new locks. 2PL guarantees serializability, more on that later. However, it can lead to deadlock. Asterisk strict two-phase locking, strict 2PL a stricter version of 2PL. It holds exclusive locks until the transaction commits or aborts. Strict 2PL also guarantees serializability and prevents cascading rollbacks. Asterisk conservative two-phase locking, conservative 2PL a transaction acquires all locks it needs before it starts executing. This avoids deadlock, but it can be inefficient. 5. Code example, implementing strict 2PL in a simplified system, pseudo-sql and Python. Let's illustrate strict 2PL with a simplified example. We'll use a dictionary to represent the database and Python functions to simulate transactions and locking. This is a conceptual representation and wouldn't be used directly in a production DBMS. Explanation of the code asterisk. One database dictionary asterisk simulates the database. In a real DBMS, this would be a database connection. ToLock class asterisk represents a lock associated with a data item. Acquire_shared, acquires a shared lock. It waits if an exclusive lock is held. Release_shared, releases a shared lock. Acquire_exclusive, acquires an exclusive lock. It waits if any shared or exclusive locks are held. Release_exclusive, releases an exclusive lock. 3 lock_manager dictionary asterisk stores the locks associated with each data item. Keys are data item names, example account 1, and values are lock objects. 4 transfer_money, function asterisk simulates a transaction that transfers money between 2 accounts. Acquire exclusive locks, strict 2PL the function first acquires exclusive locks on both from_account and to_account before reading or modifying the data. Lock ordering is implemented to prevent potential deadlocks. Lock ordering asterisk to prevent deadlock, the locks are acquired in a consistent order. We sort the account names alphabetically and acquire the locks based on this order. This ensures that all transactions try to acquire locks in the same order, preventing circular wait conditions. Perform transfer asterisk the function reads the balances, performs the transfer, and updates the balances. Release locks, strict 2PL the function releases the locks only after the transaction has either committed successfully or rolled back, although the rollback is not fully implemented in this simplified example. This ensures strict 2PL. Error handling asterisk a try, except, finally block is used to handle potential errors and ensure that locks are released even if an error occurs. 5 run_transaction, function asterisk a helper function to run a transaction and print the result. 6 main execution, if __name__equals __main__:. 3 threads are created, each simulating a concurrent transfer. Threading.thread, used to create threads for concurrent execution. Thread.start, starts the execution of the thread. Thread.join, waits for the thread to complete before continuing. Database state * finally, it prints the final state of the database. Important notes * deadlock * This example includes a simple lock ordering mechanism to mitigate the risk of deadlock. Deadlocks can still occur if transactions try to acquire locks in complex ways. Real DBMSs use deadlock detection or prevention techniques to handle this. Rollback A proper rollback mechanism is not fully implemented in this simplified example because the database is in memory. In a real DBMS, the rollback would involve undoing all the changes made by the transaction. Simplified * This is a highly simplified representation of concurrency control. Real DBMS implementations are far more complex and optimized. Database connection * In a real-world scenario, you would replace the database dictionary with a proper database connection, example using Psychopage 2 for PostgreSQL or MySQL.connector for MySQL. 6. Other concurrency control techniques ****. Timestamp ordering ***. Each transaction and data item is assigned a timestamp. Transactions are executed in the order of their timestamps. If a transaction tries to read a data item with a timestamp later than its own, it is rolled back. If a transaction tries to write a data item with a timestamp later than its own, it is rolled back. Timestamp ordering avoids deadlocks but can lead to starvation, a transaction repeatedly being rolled back. Optimistic concurrency control ***. Transactions proceed without acquiring locks. At the end of the transaction, the DBMS checks for conflicts. If conflicts are found, the transaction is rolled back. Optimistic concurrency control is suitable for environments where conflicts are rare. Multi-version concurrency control, MVCC. Each data item has multiple versions, each with a timestamp. When a transaction reads a data item, it reads the version that was current when the transaction started. When a transaction writes a data item, it creates a new version. MVCC avoids read-write conflicts and provides high concurrency. 7. Serializability ***. The goal of concurrency control is to ensure that the concurrent execution of transactions is equivalent to some serial, sequential, execution of the same transactions. This property is called serializability. Serializable schedule ***. A schedule is serializable if its effect on the database is the same as some serial schedule. Conflict serializability ***. A schedule is conflict serializable if it can be transformed into a serial schedule by swapping non-conflicting operations. Two operations conflict if they access the same data item and at least one of them is a write operation. 2PL, and strict 2PL, guarantees conflict serializability. 8. Conclusion ***. Concurrency control is a complex but essential aspect of DBMSs. It ensures that multiple users can access and modify data concurrently without corrupting the database or violating data integrity. Locking, timestamp ordering, optimistic concurrency control, and MVCC are common techniques used to implement concurrency control. Understanding these concepts is crucial for building robust and reliable database applications. This tutorial provided a basic introduction and a code example to get you started. Remember to explore the documentation of your specific DBMS for detailed information on its concurrency control mechanisms.